Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Colton Burross and Krista Lynne Smith with us today. Hello, Colton. Hello, Krista.
Hello.
Hi.
Colton, let's start with you. What's your geolocation? Are you actually where your background picture
No,
appears?
I'm not in
Oh,
Cologne, Germany.
rats.
I'm actually across the hall from Professor Smith. So I just wanted to have my own screen.
Ah, it's very cool, very cool. And Krista, what's your geolocation?
Yeah, so we are both in College Station, Texas, where we're experiencing a May heat wave. It's like
Okay.
103. So
Woo!
yes, it's definitely pre-summer here.
Well, congratulations. You're hotter than Phoenix on this May 15th of 2025 as we record this. So we're actually fairly pleasant today, at about 80 something. So yeah.
Lucky.
Yes, how about that? Very good. And Krista, what do you like to do for research?
So I study active galactic nuclei generally, so all kinds of phenomena that have to do with supermassive black holes,
Mhm.
from kind of the accretion physics very close to the black hole itself to the impact that it has on its host galaxy.
Very cool. And Colton, how about you? What do you like to do for research?
I just pretty much do what she gives me, though. And but I like anything on black holes. I'll do.
Cool.
But Colton did work on supernovae a little bit before
Yeah, I
before.
did though.
Okay, and so let's ask Colton, what is your current position?
I'm a research assistant for Professor Smith here at in the Physics and Astronomy Department at Texas A&M University.
Uh-huh, very cool. And I think you just finished up your undergrad.
Yeah, I did last August though, and I'm doing this to prepare for grad school
Very
because I
cool.
wanted to have research done before I apply.
Yeah, very cool. Very nice. Beautiful. And that is going to bring us to this very awesome research note. It is open access. It's the open access era, people. You can go grab a copy, go get one for free. Sub-parsec detectability lifetimes for a sample of dual AGN with known mass ratios. And Colton, Krista, take us away.
Okay. So I'll give a little bit of background and then I'll let Colton kind of explain the details.
Mhm.
So we eventually are going to want to look for the gravitational wave signature of merging supermassive black holes,
Yes, low frequency.
yes, throughout the universe. And in order to understand the signal from the least emission, which is mentioned here in the abstract, um, in order to understand the signal that we will get from Lisa, it helps immensely to have priors. So to understand what we expect from the population of binaries, and the signal that comes from those black hole binaries depends on the ratio of the two masses of the black holes, their
Uh-huh.
spins and their separations. Uh,
Yes.
so I'll let Colton explain a little bit about what we did, and if you need help, Colton, no problem. I'm happy to help out.
Yeah, so I just took the all the entire sample from the Foreman paper.
Cool.
That's referenced in in our paper though.
Yep.
I just took that and I just solved for the mass ratio, and then I would just plug it in. Then I would just plug it into the equation we're using here to get the sub-parsec lifetime.
Okay, let's see. Do, do,
Yeah.
do.
So this lifetime
That was
equation,
the.
yeah, go ahead, Colton.
Now you go ahead.
Okay. This equation is the length of time during which during which a binary pair of AGN, which is a very, very close by pair,
Uh-huh.
um, is detectable using a particular spectroscopic signature,
Okay.
which is offset broad emission lines. And that's when the broad emission line profile peak is not at the same velocity location as the narrow line peak.
I'm with you. Hmm.
And that is a common way to look for very, very close separation binaries,
Yeah.
because at these separations, they are not separate. They're not in separate galaxies anymore. This is way after the merger has happened.
Okay.
So the letter Q in this equation is the mass ratio. So M2 over M1.
Yep.
And so the length of time that this signature is viable is dependent upon the mass ratio Q and then the little exponent up there, lambda, which is the Eddington ratio, the accretion rate.
Okay. I was going to ask which Eddington ratio. Okay.
Yeah, so this is the actual mass accretion rate divided by the Eddington limit mass accretion rate.
I'm with you. Yep. Mm-hmm. I have one question on that expression, just out of curiosity. Do those exponents come from a fit, or are they from a theoretical expectation? Where does the 3/4, 3/8, and -5/8?
So the Bogdanovich paper there, Bogdanovich 2008 in the abstract,
Okay.
is a modeling paper, and that's where you can see the results here. So it is, sorry, not the abstract, the bottom of the introduction. My bad.
Oh, there we go.
Tamara Bogdanovich's paper. So it is it's quasi-empirical because it's from a set of simulations and not analytics, but that's what you get out of the scaling.
Okay, thank you.
Yeah. So Colton, maybe we talked about this a little earlier. You could talk about why did we do this with the Foreman sample?
Why we did the Foreman sample?
Yeah, what are they? Why those instead of a binary sample that's really close together?
Oh, it's because we actually had the masses. We actually had the masses that we could use to calculate the mass ratio for each pair.
Right.
Okay.
Because these galaxies in the Foreman sample are not binaries that are really close together. They're duals. So these are galaxies that are really far apart still, but are merging.
Okay.
In that case, we actually, like Colton said, we actually can measure the two separate masses, which you can't do in the binary case because
you can't see them. Right.
You can't see them.
Right. Okay.
So our goal
Okay.
was to measure a realistic distribution of this lifetime for a realistic population of mass ratios.
Mm-hmm.
Yeah. And Colton, maybe you could say a little about what these represent. What will these eventually become, these Foreman galaxies?
I mean, dual AGN, right?
Yeah. And they are the precursors, right?
Yeah,
they're the precursors of the binaries. So if we assume that, the little binaries that are out there today that Lisa will see used to be
this far apart,
these far apart pairs, then we can use these pairs to kind of get a realistic idea of what the mass ratio of binaries actually is.
And let's see. So this is Lisa. So these are going to be low frequency gravitational waves?
Yes, that's right.
Okay.
Very low.
Okay. And well within the Lisa band, yeah?
Well within the Lisa band. In fact, if they're not in the Lisa band, they're out in the pulsar timing band. So they'll be quite low frequency.
Oh, very good. Yeah. Cool. Okay. So we've got some tables, we got some masses, we created a calculated Q, banged out a lifetime. So we can see how many of these we might expect to see with Lisa. Okay. I'm with you.
So yeah, this part of the paper just describes what you see in the plot. So I guess if we look at the plot, maybe that's the place to hang out for now.
Yeah.
So Colton, maybe say a little bit about what you did to get this plot. However you want to describe that.
Yeah, so can you zoom out a bit though, so I can zoom out a bit so I can see the full thing? Yeah, okay, stop right there. So yeah, we did three different Eddington ratios though, and it's color coded though. Yeah, so I calculate. For each pair, I did three calculations. I did three calculations per pair, depending on the Eddington ratio, and that's just showing the frequency where it's at in the lifetime of it. You can see that, of course, the biggest outlier you can see though is that the Eddington ratio of 0.1 seems, well, that one's an outlier of 19 frequency. It's like it's in the ballpark of like 50 years, 50 MY, 50 M year.
Thank you. I was going to say 50 years. We're never going to observe anything.
No.
50 mega years, yeah.
Yeah, 50
Call it a
mega
transient.
years.
We'll call it a transient. How about that? Okay. Okay, good. I'm with you.
Yeah, just the distribution of mass, the distribution of mass ratios. Of course, it's like right there, the smaller table within the table,
Okay.
or the
Uh,
smaller chart within the chart
Yeah.
got it. So the
graph.
inside here is the frequency versus the mass ratio. And this is directly what you compute with from the Foreman. Yeah.
Yes, sir.
Right. Okay. Um, let's see. Here's a point
So
6.
yeah, we have quite a
Okay.
spread of
Okay.
detectability lifetimes.
Uh-huh.
Mm.
From
Out
very
to a very
small.
large number, but mostly around mostly less than 300 million years.
Yeah.
Um,
Okay.
which is pretty encouraging, actually. That's a good long time, and I think this lifetime is nice for what we might be able to apply to spectroscopic surveys, um, and
Oh, yeah.
how many objects we
Yeah, yeah.
expect to find in a given spectroscopic survey.
Mm-hmm. 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 Very cool. Very nice. Nice work.
Thank you.
That was awesome. Short and sweet, and I love it.
Yep, that's why we love research notes.
That's why we do.
Yep,
So, Colton and Krista, I want to thank you so much for walking us through your very lovely research note.
no problem.
And of course, one figure and one sample will open up all kinds of possibilities for where this might go. So go ahead and let me ask, and what do you think are both sort of immediate next steps on building on this work, and then maybe perhaps a little bit longer term? So, are there additional samples that one might wish to apply to? Is there a set of direct observations you could go against, and so on? So, just sort of next steps.
Yeah, so we can certainly apply this to more samples. So we started with the Big Mac catalog, right, Colton?
Yeah, that's correct.
And you found a few different papers in there that had different binary samples, right?
Yeah, I mean, we were looking at the Graham paper though, that
Mhm.
was in the Big Mac though, but we shelved that to get this done faster.
Yeah, so the Big Mac is the big multi-AGN catalog is what
Right,
that stands for. And
right.
it's compilation by Ryan Fifley of, all the multi-AGN that have been detected using all kinds of different methodologies.
Okay.
And to do this calculation, we just need mass ratios. So nice separation between the galaxies is necessary. But there's lots of other samples in the Big Mac that were detected in different ways that we could potentially do more detectability calculations for.
Okay.
So this was a little bit of a precursor to that.
Mm-hmm. Mm-hmm.
Um, and I'm on the science team for the LISA mission. So kind of the goal here is to get these statistics ready to go so that we can apply them to things like the LSST data that'll be coming in soon from Rubin Observatory, and other time domain surveys and stuff that are going to look for periodicities, which is another way of finding binaries,
Yep.
apply spectroscopic searches to the LSST sample to see what they're doing in periodic time. So the same signature that gives rise to this offset broad line is a time domain signature. So the broad line actually
Right.
moves with time
Right.
as the black holes orbit each other.
Yep.
So what we hope to do is use work like this to predict the number of binaries with different mass ratios that we will be able to detect in upcoming time domain surveys in order to set priors for what we'll see with the LISA mission.
Okay. Okay. And the idea with the Lisa, just to say it, the idea is to detect each of these as individual systems, not
Um,
broad background.
no, yeah, so it's a statistical background, right?
Background. Okay.
So there will be probably,
So the more
we
there are,
hope
the
we
bigger
hope
the
very
background.
much that there will be actual mergers during the mission lifetime
Ooh.
set
Ooh.
where we see a chirp like you do with
Yeah, yeah,
light,
yeah, yeah, yeah. Neutron
but
stars.
most of the signal will be a background
Broadband. Mm-hmm.
from all these pairs that are circling each other and putting out these ripples in space-time. And that's the same background that the PTA, the pulsar timing arrays, have reported seeing
Uh-huh.
a
Mm-hmm.
hint of
Mm-hmm.
in recent years.
Nanograph. Yep. Mm-hmm. Mm-hmm. And of course, the more of these there are, the bigger the background. So yay.
Yes. And Colton hopes to go to Potsdam to study, to go to grad school to study black holes and gravitational wave physics and stuff like that.
Awesome. That'll be very cool. Very
Mhm.
nice. Well, this is going to be really exciting to see this develop over the next couple of years, both as we, simulate, model what we expect to see in the build up to LISA and all of the great observatories coming up in between. So it'll be really exciting to see this develop over the next couple of years.
Definitely.
Very cool. All righty, Colton, Krista, I want to thank you so much once again.
Thank
And
you.
that will do, oops, and that will do
Yeah.
everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Thank you.